Hi folks, welcome back to Physics with Captain Rod. Making this video here to help you out with number 36 in Chapter 9 in your OpenStax textbook here. So it says, let's see, two identical pucks collide elastically on an air hockey table. I have already drawn a series of pictures here, and the picture that they have in the book, it kind of looks one-dimensional. Looking at this problem, I think that the picture's kind of screwed up. I believe this is a two-dimensional problem. I'm just going to ignore the picture that they have. It says that two hockey pucks collide on an air track table. This first picture here is a picture just before impact. I'm going to imagine this guy is at rest, this guy's moving along in this direction, and what I'm going to do here is I'm going to put a momentum vector in for it, and then I'm going to label that vector MAVA1. I'm now inherently calling this mass A, this guy mass B. And because it's a momentum problem, principles of impulse and momentum is where you start. So what we want to do, or what you want to do with this problem, is draw your momentum vectors here before impact. This middle picture represents what's happening, what I always call like from 1 to 2. I'm calling this one over here picture 2. The middle picture here is for our impulses. And this contact point right here is going to give us impulses basically this way on the green mass, this way on the red mass. That's because we have surfaces in contact here. These forces are normal forces. So this impulse is going to look something like N delta T, and this one, N delta T. And I'm just calling that force N because it's a normal force applied right at this surface. Picture 2 here, this guy's momentum vector, it says something like scattered to an angle of 30 degrees with respect to its incoming velocity. So this guy right here is going to scatter to an angle something like this. There's its momentum vector. I would label it something like, I guess I call that mass A, maybe MAVA2. 30-degree angle with its incoming velocity vector. This guy is going to have to do maybe something kind of down and right. So I would label that momentum vector maybe MBVB2. This angle here, at first right now, I'm going to call that an unknown angle. So you start by drawing an impulse momentum diagram, and I basically have done that for you. This, as I kind of glance through the diagrams, this picture here is not a problem because these impulses are internal to the system. As long as we define our system, both objects together, that's an internal impulse. You don't need to worry about it. So this diagram right here is not going to yield anything in our equations. When we look over to the right, that velocity is an unknown, so is this one, and so is theta. So there's 3 unknowns in this problem. That means you have to write 3 equations. One equation you can write is a momentum equation, x direction. I'm just going to put a little arrow here for the direction I'm calling positive. So what you're going to do is you're going to take the momentum in this picture in this direction, MAVA1. This guy doesn't have any momentum, right? Plus your impulse. Well, there's no impulse in that picture. That's because the net force here is 0. Equals net momentum x direction. The x component of this guy's momentum vector would be MAVA2 cosine 30. Now, this is one of the 3 equations you're going to have to write here for this problem. I'm going to talk about how to do the rest of them, but I'm not going to do any more because that's basically for you folks to do. You're going to write a momentum equation in this direction as well. When we look over at this picture, ask yourself, how much momentum does this have in the y direction? And there's a numerical answer to that. And this guy doesn't carry any momentum, so that should tell you what the first term is. No impulse in the y direction. There's actually no impulse in this problem in any direction. Right-hand side, this momentum vector has a y component, which is this way, and it's positive. Notice it's opposite the 30-degree angle. This momentum vector has a y component here opposite the angle I called theta. So you need to put that together, write an equation. It'll look similar to this. Now, that's only 2 equations once you have that. So I'm going to let that line represent that second equation. The other equation we can write is an energy conservation. If you look carefully in the problem, it says collides elastically. Because it's an elastic collision, that means you can equate the kinetic energy in this picture to the kinetic energy in this picture and write that equation out. That equation should have 1 term on the left and 2 terms on the right. What you'll then have is 3 equations, 1, 2, 3. and three unknowns, VA2, VB2, and theta. I think it's going to be a tough system to solve because it's very nonlinear with that theta there, but have at it. If you have any trouble, ask and I'll help you out with it. Hope that helps with number 36. Have a great day.